Hello, everyone. It is me, and like I told you, my class, the audience tonight is global. We have reached an international audience, and so if you feel inclined to comment below, please do so with the international audience in mind. So, as I said today in class, the important part about this screencast is that you really understand the next part of this story, so to speak. Take out those notes that I asked you to take out for this screencast, and you'll notice the first part of it is just like my screen right here, okay? So let's begin, and I hope that you're all having a lovely evening as you enjoy the viewing to come. So the first question is, why are polynomials so nice? Why do we love them so much? And why is it when we leave the set of polynomials, things get a little bit hairy? Well, you may remember polynomials, of which linear and quadratic functions are a part of. Polynomial functions are continuous and differentiable for all real numbers, right? They're continuous and differentiable. They have a domain of all real numbers. We spent time, even as early as, let's see, TFA and TIC, looking at things like relative maxima and minima. They're incredibly predictable. They are not at all risk-taking. They are very predictable. They have a predictable, really everything, right? There's nothing about them that makes us afraid. When you leave the world of polynomial functions, we enter a realm that allows us to have asymptotes, discontinuities, domains that are not all real numbers. We have periodicity. We have, let's see, infinite asymptotes. So when we leave the world of polynomial functions and we enter the world of, say, exponential functions, sinusoidal functions, logarithmic functions, rational functions, we encounter those annoyances. Now, you know me, I don't actually think these are annoyances, but they are things that we have to attend to that we didn't have to attend to in this world of polynomial functions. And this world of non-polynomial functions, when you leave the world of polynomial functions and you enter the world of what are called transcendental functions, and this is such a lovely word. Transcendental functions is a pretty complicated definition, but for the purposes of us tonight, I'm just going to say that transcendental functions for us right now, they are not polynomial functions. They, in effect, transcendental functions transcend that which polynomial functions occupy. They transcend the world that polynomial functions occupy, which means they go above and beyond, right? So a really great analogy that I think is apt and also humorous is that of, like, you know, the date you bring home to meet your parents. When you bring home a date to meet your parents, or when your date brings you to their home to meet their parents, you want to be a polynomial function because polynomial functions are reliable, predictable, they're not risk-taking. If you really wanted to spend time with a polynomial function, you would just be soothed because nothing scares you. You don't want to be a transcendental function because once you're a transcendental function, the parents are going to have their radar up and say, why are they asymptotic? Why do you have holes? Why do you have this thing called a period? And why isn't your domain all real numbers? I only want my child to be with someone whose domain is all real numbers. I don't like the fact that you're not all smooth, okay? So this is really a really introduction to the next chapter in our story. Now notice here, ladies and gentlemen, and global audience, I did not write anything down here. Hopefully you will be moved by this introduction, that you will then enter your own narrative based on what we just talked about, or based on what I just talked about, okay? So let's now move on to how this relates to you. Well, first, again, we have some appetizing intros, okay? We're going to go and define this term that looks very frightening, this term in a moment. For the moment, just ignore that, okay? This is old news. Let me shrink it down a little bit. The old news here is, just look at the black typed print first. All of this is old news. It says, if we're given some function, we know that if you're to find the local linear approximation of f of x at x equals 0, and yes, I am making that criteria right now at x equals 0. Of course, we have found equations of lines tangent to the function at values beyond x equals 0, but for right now, I want to just keep it at x equals 0, okay? So we know that if we were to find the equation of the line tangent to f of x at x equals 0, we would come up with the function p of x, and it looks like this. P of x is f of 0 plus f prime of 0 times the quantity x minus 0, or as you can see what I did here, I just merely distributed this to the terms, and here's what I have for p of x. Now, depending on how fresh you are, some of you may be wondering, where on earth did this come from? I don't remember. Well, let me take you through, okay? When we found the equation of the line tangent to f at x equals 0, we were looking primarily at finding a line, right, that had two things in common with f of x, right? So in this build-up here, I'm calling p of x the equation of the tangent line, okay? So when we found the equation of the line tangent to f of x, or what I'm calling here p of x, there were two things we wanted to have in common with the function. Number one, that tangent line had to have the point of tangency in common, of course, right? Of course it does. The tangent line has to have the point in tangent in common with the function. And specifically, we know that that tangent line would be, because I told you it's x equals 0, and then whatever the y value is at x equals 0. So we want the point of tangency to be in common. The other thing we want to have in common between the tangent line and the function is f prime of 0, or the slope of the line tangent to f of x at x equals 0. And if I go over here, just do a quick sketch over here for a second, you know, none of this is surprising. It may be foggy, but it's not surprising. Like if this is f of x, for example, right? You know that the tangent line is going to look like this, because the point of tangency for now, we're just calling it x equals 0, right? So as you can see, this pink line here has the point of tangency in common with f of x and the f prime of 0 in common with f of x. So we want the line to have the same f prime of 0 value. So again, this is all old news. The tangent line equation, and we all just drop into point slope form, is y minus y naught equals m being f prime of 0 times x minus x naught is 0, because the premise of all this is that x naught equals 0. And then what I did here is I solved this for y, so y equals f prime of 0 x. Of course, this distribution yields 0. I added 0 over, and let's just not be confusing. Miss Yam called this p of x, right? So I guess I could even call this p of x if you want this to all make sense, right? Okay, and so what we did was we called this the local linear approximation of f of x at x naught equals 0. Okay, so all old news, but so very important to lay the foundation for the next chapter of the story. Oh, before I move on, you know, we know that a local linear approximation is a line, of course, and what we did here really was we found the equation of the line in the generic form, if you will, y equals mx plus b, right? I mean, y equals mx plus b is just the generic equation of a line. And what we found here were kind of the m and the b values, if you will, okay? Just a little minor point. So now the rest of the story is now new. Now we enter this terrain, okay? And as you listen to this screencast, hopefully you're wondering, wait a minute, what on earth does this have in common with all the series and interval of convergence stuff we've been doing? And I'm so glad you asked that or thought that, because hopefully the answer will come in about, well, 3 minutes, okay? So here's my question. What if we wanted to have more in common between f of x and its approximation? In other words, what if I wanted to have more in common than just these two criteria? What if I wanted to find not a local linear approximation, but I want to find a local quadratic or parabolic approximation of f of x at the point of tangency? And again, yes, I'm sticking with at the point of tangency being x equals 0. All right, before I move on, let's just take you over here for a little graphic shot for a second. Okay, so let's say that I have, a function that looks like this. This is f of x, right? And if I'm looking at the tangent line approximation of the function at x equals 0, it looks like this. Here's a tangent line, right? Okay, that's nothing new. But if I want to kind of just think about, well, what's a parabola that would really approximate f of x at x naught equals 0? Well, the parabola maybe would look something like this. It wouldn't be a line necessarily. Oh, my stars, what is my poor parabola? Let's just undo that and pretend we didn't see such blasphemy. Let me try this again. Maybe the parabola may look something like this, right? Okay, and again, this is just for you to get an intuitive sense of the fact that it's perhaps the case that a quadratic approximation would be better than a linear approximation of f of x, because as I choose x values close to the point of tangency, the parabola is quote unquote closer to the function, right? But this is just kind of more of a visual sense of what I'm doing here. So let's say I want to find a local quadratic approximation of f of x at x equals 0. And I gave you all a reminder here, just as we talked about in the previous model, that this is the generic linear function. I'm giving you a reminder, a generic quadratic function looks like this, okay? In addition to the characteristics that the approximation and the function share with respect to the linear one, we want to add another shared characteristic that the approximation would have with f of x. So what are those three characteristics? Well, the first two, I literally, you know what I did here? I literally copied those two criteria from here, because I want to maintain those two criteria, that the point of tan is the same and the first derived value at x naught is the same. But then I want to add a criteria, and the criteria, yes, you guessed it, that I want the approximation to share, in addition to the first two criteria, is the f double prime value at x naught. So here's what I'm doing. If you look at this, I want the approximation to share the same f of 0 value, the same f prime of 0 value, and the same f double prime of 0 value, or the concavity value, okay, at x equals 0, the point of tangency. This whole conversation tonight is all about shared characteristics at x equals 0, the point of tangency. I know that I think like someone like Melissa or Max, they're just itching because they're wondering, what if x naught was not 0? And as I always promise, I will never leave you hanging. I just haven't gotten there yet. I should say we just haven't gotten there yet. So just settle in and everyone just relax. Okay? So that's the crux of this. The question is, if I increase the degree of my approximating function, first, how do I do that? All right, here we go. So the goal is to find the local quadratic approximation, that's what it's called, the local quadratic approximation in this form, okay, of f of x at x equals 0. All right, so we want the point of tangency to be in common. So look at this argument right here, so follow me. I want the point of tangency to be in common. So what I'm saying is f of 0 needs to equal y of 0. And what I did here, look what I did, right? If y equals ax squared plus bx plus c, when x equals 0, right, when x equals 0, the y value on the parabola, we want to be the same as the y value on the function. And when I do that, you notice 0, it kind of zeroes out this term and this term, and we're left with c equals f naught. That's very convenient because now look what I found. I've actually found the c term of my quadratic approximation. Okay, but I also said I wanted to have the first derivative value at x equals 0 in common. So what I'm saying here, and look at my notation, all the minutia, one of our favorite words recently, or at least my favorite word. The first derivative value at x equals 0 being in common says f prime of 0 needs to equal the derivative with respect to x of the quadratic function at x equals 0. And notice what I did here. See how I just dropped the c value in because c equals that? Well, let's see. D by dx of ax squared plus bx, right? If I take d by dx of ax squared plus bx, that will just give me 2ax plus b plus 0, of course, because this is a constant, and d by dx of a constant would yield 0. And then to address the d by dx at equals 0, look what I did. I plugged in x equals 0 here. At the end of the day, oh, interesting. I get f prime of 0 equals b. Again, that's very convenient because now I've made some progress. My local quadratic approximation looks like y equals ax squared plus f prime of 0. Oh, f prime of 0x plus f of 0, because I found the b and c values. What's left to find is the a value, and that's where my third criteria comes in. This new criteria, I want the second derivative value at x equals 0 to be in common. That means f double at 0 needs to equal the second derivative of the quadratic function evaluated at x equals 0. And notice, you can see here how I dropped already in. I dropped in the b and the c, right? Okay. And again, let's just take a little step over here. D by dx of ax squared plus f prime of 0x plus f of 0. This just will equal 2ax plus f prime of 0, right, everybody? But then I want to take d by dx of this, which will then equal 2a, and derivative of a constant just becomes 0. So that's where I am right here. So f double of 0 equals 2a plus 0, or a equals f double of 0 all over 2. And at the end of the day, what I have found is, you know, just like there's a formula for my local linear approximation, right? I just found the general form of a local quadratic approximation. A local quadratic approximation of f of x at x equals 0 is right here. Look at that, where I have found the a, b, and c values. What a treat. What a treat. So now I'm going to give you some vocabulary, okay? What I'm going to do over here is something convenient. I'm just going to pull this over, okay? I'm going to take this local linear approximation and just move it over here so I can see something. Pardon my shrinkage here for a second. I'm going to pull this down here, okay? So there's my local quadratic approximation. Here's my local linear approximation of f of x at what point of tangency, everyone? Yes, it's at x equals 0. That equals f prime of 0x plus f of 0, okay? Maybe some of you are seeing a pattern already. I don't know. Maybe some of you are. To assist you in seeing this pattern, and if you are listening to this with someone and you see the pattern, please don't yell out or scream or hit anything, because it just ruins the experience for the person you're watching this with. You want them to have the adrenaline rush and the exhilaration that you are experiencing. Ladies and gentlemen, all I'm doing here is just rewriting the terms, okay? All right, well, I see this, I see this, I see that. I'm going to do something else to kind of make this even more fun. Okay. 2 is the same thing as 2 factorial, right? I'm going to do this. I'm going to do this. And I think you're all going to see the pattern. Look at that. Do you see the pattern? The local quadratic approximation, right? We end with a degree 2 term. Notice the degree of the x matches the number of derivatives. Really interesting. This is a very odd thing to write, but there is something called the 0th derivative of f, right? Which is just the function value. But I'll just do that just to make explicit the pattern here. Okay? The power of x matches, it's called the order of the derivative, and the factorial of the denominator. So while I could go through and do a large scale proof where we find the generic cubic approximation, if you were to make a guess as to what the local cubic approximation of f of x at x equals 0 would be, well, let's see if we can think about it. It would look like this. And maybe some of you are already kind of into the pattern mindset and you're just kind of do this automatically. That's perfectly fine. Okay, maybe you'll even do this, which is such a weird thing because x to the 0, of course, is 1, right? Okay, that's the local cubic approximation of f of x at x not equals 0. Now, let me go through here and say this. What is the local nth degree polynomial? Why is Miss Yam calling these polynomial approximations? Oh, I know why. Okay, why is Miss Yam calling these polynomial approximations? Well, because this, oh my stars, I just scratched it out. I meant to highlight it, oh dear, okay? This is a polynomial of degree 2, our basic parabola. This is a polynomial of degree 1. This is a polynomial of degree 3. In fact, polynomial approximations, or these approximations in general, all of these local quadratic, local linear, local cubic, they're all polynomial approximations. So here's my task for you. I'd like to write out the local nth degree polynomial approximation of f of x at x equals 0. Let's do this part together. And maybe you're someone who is comfortable, you know, going here. Maybe you don't need the 0 factorial and the 1 factorial anymore. That crutch perhaps is something that you don't need. Maybe you do need it. Whatever you need to do, just go ahead and do that. Okay, I'm going to do this, everyone. Plus dot 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 plus. Now, if it's degree n, and it is degree n, my last term here should be what order derivative of f at 0? Yes, the nth derivative of f at 0 times x to the what power? N, all over n factorial. Now, here's what I want you to do. You're going to do this, pause me, and then replay me for the answer. What I'd like you to do, everybody, is to write this series, and notice it ends at degree n, as a sum in summation notation. Do that and then replay me, please. Okay, you may have used different letters, but let me explain to you what is very important. Since here we ended at the nth degree, right? This upper index has got to be n. Okay, so whatever is changing integrally, I called it K, maybe you called it Q, maybe you called it T. Whatever is changing integrally, I have it starting at 1 and ending at N. Uh-oh, Miss Yam made a mistake. I shouldn't be starting at 1 if my my sum in looks like this. I have to start this at 0. Oh my gosh, yes, starting at 0, okay? K starts at 0 and ends at N. I will say maybe you're someone who wanted to start at K equals 1 and then end at N, in which case you'd have to do this. The K minus first derivative of f at 0, x to the K minus 1, all over the quantity K minus 1 factorial, okay? Either of these are fine. Now, here's the thing, everyone. Notice I said degree N, right? But if I were to do this and add a ... implying I want to go to the infinitieth degree polynomial, which is a very odd idea, I would change this upper limit then to positive infinity. But we'll go there together as a class. Tonight's viewing is just to kind of whet your appetite. I end with some vocabulary. And here it is. We could be very verbose about describing this. This is the degree 2 polynomial approximation of f of x at x equals 0. Or we can call this a Maclaurin polynomial approximation of f of x. What does this word Maclaurin polynomial approximation of f of x mean? Well, the word Maclaurin polynomial implies that x naught, the point of tangency, is always equal to 0. Maclaurin polynomial approximations is just another way of saying the point of tangency is that x equals 0. Whoops, I should say this is a second degree Maclaurin polynomial approximation of f of x, okay? This here is a degree 1 or first degree Maclaurin polynomial for short. Sometimes we'll even become very casual that will kind of drop this part of the phrase because it's implied. This is a degree 1 Maclaurin polynomial. This is a degree 3 Maclaurin polynomial. Okay, so degree 3, well, the degree number is obvious. This word Maclaurin polynomial just says and specifies that x naught equals 0. And with that, I bid you good night. I will see you tomorrow. And my class, I 100% will be doing a conversational, impromptu check for listening comprehension. Good night.